Continuing on with our theme of how rocks can actually be used to reconstruct and look at what's happened in Earth's past. We finished last time looking at our basic geological principles and concepts of relative age and superposition and those types of laws. Now we're going to jump into what we call, or what are known as, unconformities. Understanding these, they're a little more complex, they're a little harder to understand, which is why I'm going to do them separately as their own video. So unconformities, basically what an unconformity represents is a break in the geologic record. So rocks aren't going to continuously form forever and ever on top of each other. Occasionally something interrupts those processes. So whenever the rock formation itself is interrupted, eventually what can develop over time is what's known as an unconformity. So again, it represents a break in the geologic record, and this happens when either rock layers are eroded, so they were there, they were eroded, now they're not there, or when sediment is not deposited for a long period of time. So either the rates of sedimentation slowed way down to the point where they were non-existent, or for some reason or another, perhaps the body of water dried up and you no longer had that deposition to create new rock. And maybe it was an arid region, so there wasn't much erosion. So there could be lots of reasons why this happened, but either way, it's either because rocks were eroded, or there's just nothing going on for a really long period of time. So to do this, instead of defining each of them for you, I'm going to explain this by animating them more or less. So the first type of unconformity we're going to talk about, there are three types. The first one we're going to talk about is disconformity. Disconformity basically happens when you have the deposition happening, so you're creating your rock layers, and as you can see based on this image, rock layer 4 would be the last one that was created. For some reason or another, the body of water either goes away or something happens, or maybe either way, whether or not there's nothing deposited, or in this case we're going to say layer 4 gets eroded because it's now on the surface. Once it gets eroded, that rock layer is no longer there. So that's part of the rock record that is now missing. And if a body of water returns and you now have that deposition start up again, you get a new rock layer to form, but it is not on top of what last formed. It's that previous layer that formed is gone. It's just missing from the geologic record. So if we looked at it in this case, that dashed black line would represent what we call a disconformity. That dashed black line represents a big jump in time between layer 3 and layer 5. So, I mean, some examples, disconformities are hard to find a visual representation because the layers are typically still horizontal. So you can't just look at the rock layers and identify it as a disconformity typically. But in this case, we're looking at an image of a disconformity, and we have this moth type thing that's labeled as 290 million years old in the purple layer, and then just below the red line we have this trilobite that's 490 million years old. So from the purple layer to the orange layer underneath the red line, you're talking about a gap of almost 200 million years, which is a big jump in time, and that would be your disconformity. So it's the actual contact between the layers where that gap in time exists. The next type, angular unconformity. This is the easiest to identify. Basically, you start off with rock layers in their horizontal positions, you have that sedimentation occurring, and this time when you have that uplift and the body of water goes away or it is evaporated, they don't just uplift, the rock layers also tilt. Alright, so these rock layers are now disturbed. You can no longer relate these layers from one to another, saying that the one on top is youngest and the one on bottom is oldest, because they're now disturbed. So what happens once they're exposed on the surface, you get a little erosion. So now the angled layers are exposed on the surface, and if the body of water returns, you can get a new horizontal layer to form on top of those angled layers. So the actual contact between the angled layers and the horizontal layers represents your angular unconformity. And that would also represent a huge gap in time, because this would take millions of years to develop. So looking at this, this is again one of the easiest to identify. Here's an example. You can clearly see it. You have these angled layers underneath, and then right on top you have these horizontal layers that are in contact with them. So this line right here between the angled layers and the horizontal layers represents your angular unconformity. This is also the same type of unconformity that made James Hutton very famous. I believe it's called Seeker Point. It's somewhere in Scotland. Basically, in his travels, when he was trying to collect evidence to show that the Earth was, processes that form rocks took a lot longer than people originally anticipated, he came across this. And if you can identify it, there's actually an angular unconformity that exists in here. So you have horizontal layers going this way, and then you also have vertical layers going this way, and we get this little diagram showing between the top and bottom layers. So there's an angular unconformity that exists right here, and this is what really made him famous, was this specific outcrop and how he used it to explain what was actually happening on Earth. Moving on to the last one. The last type of unconformity is known as a nonconformity. This basically means it doesn't conform at all. So something completely different's going on. It's not the same. So in this case, this is the only type of unconformity that involves another type of rock beyond just sedimentary. So in both previous types of unconformities all involve sedimentary rock of some sort. Whether or not those layers were angled or horizontal, it didn't matter. So in this case, you start off with a scenario like this, where you have an intrusive igneous rock, or maybe an underlying metamorphic rock, or some sort of bedrock, basically. And what happens over time is the material on top of it gets eroded away. And now that rock is exposed at the surface. So if a body of water returns and you have that deposition occur on top of that, you end up with a scenario where you have horizontal sedimentary rock layers on top of a non-sedimentary rock, so either metamorphic or igneous or some combination in between those. Basically, you can find these pretty much anywhere. This is commonly, this is the type of thing you would expect to form in a lot of the lakes and lake beds around New Hampshire. So in terms of applying to what we were talking about in the previous video in relation to the Grand Canyon, these unconformities exist throughout the walls of the Grand Canyon. They're hard to identify. You can't just look at it and identify them. You need a little more evidence to help you out, which we'll get into in the next section. But looking at this, basically the red lines represent some form of unconformity. And just by looking at what's going on from one side of the red line to the next, you can kind of figure out what type it is. So in this case, we have horizontal sedimentary rock layers on top of other horizontal sedimentary rock layers. In this case, so that would be your disconformity. And the same thing here, except you can kind of see they drew in an erosion. It looks like erosion happened in this layer. Alright, so those green lines represent your two disconformities you could find inside the Grand Canyon walls, or at least this part of the Grand Canyon. Looking at the next type, again, the easiest one to identify, you have these angled rock layers, which are in contact with the horizontal rock layers above it. So that would represent your angular unconformity. And anytime you see, oh, that disappeared kind of fast. Anytime you see angled rock layers in contact with horizontal layers, you know the angled rock layers are going to be older. Okay, and then the last type, oh no, what happened? There we go. I'm back. Actually, hit the wrong one. There we go. The last type, if you look at the bottom of this image, we have what's known as the Vishnu schist. This is a metamorphic rock that makes up the base of the Grand Canyon. And then you also have a granite that cut through the schist, and these two rocks make up the bedrock of the Grand Canyon. So in this case, when we're looking at this teal line represents the boundary between one type of rock, either metamorphic or granite, that's in contact with the sedimentary rock above it. So this would be a great example of a nonconformity in this scenario. So looking at the big picture, those are the three together. All three types of unconformities exist in one place, all right on top of each other. And this would be what it looks like in real life. Can't quite see the schist at the bottom, but your unconformities exist in that massive rock. Alright.